Next is the nucleon potential in simple theory of Deuteron. We have already derived the Schrodinger wave equation for a Deuteron by considering it as a system consisting of a proton and a neutron. So this was the equation that we have derived, d square u of r by dr square plus 2m by h cross square e minus v of r into ur equal to 0, and we have already marked this as equation number 6. To simplify the analysis of the Deuteron, we will assume that we can represent the nucleon potential as a three-dimensional square well as shown in figure. So this R, which is varying from 0 to maximum value, and you can see that a square well potential means up to a distance it has a constant value, then it's suddenly becoming 0, and after that value it is again 0. This is the nature of a square well potential, and it is already known to you. So here R represents the separation between the proton and the neutron, small letter r. So capital R is the effect, R is in effect a measure of the diameter of the deuteron. So we are assuming that this capital R is the diameter of the deuteron, and up to that you have the nuclear force, and above that, so inside that the potential is a constant minus V0, and after that value you are taking as 0. The potential function providing the simplest solution of the Schrodinger equation can be represented as V of r equal to minus V0 for small letter r less than capital R, and Vr equal to 0 for small letter r greater than capital R. And this small r less than capital R can be considered as region first, and small r greater than capital R as region second. So this is the region first and this is the region second. For the ground state of the deuteron, the total energy E is negative, and the reason is that it is a bound system, and this is already known to us. When a system is a bound one, we will consider its energy as negative. So in order to separate that system, you have to supply energy, or you should give some positive energy. And as you know, the ground state energy of hydrogen electron in the ground state, you are normally taking as minus 13.6 electron volt. So that minus sign implies that electron is bound to the nucleus of hydrogen atom. In the similar way, here also our energy will be negative, and that energy which will be equal to the binding energy of that state. So if you are representing the binding energy with B, our energy we can write as minus B. That negative sign implies that it is a bound system. And for the region first, our potential energy V equal to minus V0, and for the second region, potential energy V equal to 0. The regions are familiar with us. Small r less than capital R is first region, small r greater than capital R is the second region. And substituting for E and V, equation 6 can be now rewritten as, now we are not writing that U of R, we are just mentioning it as U, which means that it is a function of R. D square U by dr square plus 2m by h cross square, in place of E we have substituted minus B, and for the first region R less than capital R, value of V is minus V0, and our equation was E minus V. So in place of E it is minus B, and here you have minus V, and V is minus V0, so you have two minus signs, so it will plus. So minus b plus v0 of u equal to 0 for r less than r. That means our first region. And d square u minus dr square. Actually it is 2m by h cross square. Here you have outside region, our b equal to, so e is equal to minus b and v is equal to 0. So we are taking that minus sign here. So it is minus 2mb by h cross square u equal to 0 for the second region. And now we are rewriting this equation as d square u by dr square plus k1 square u equal to 0 for r less than capital R. And d square u by dr square is equal to minus k2 square u d square u by dr square minus k2 square u is equal to 0 for r greater than capital R. So here this you are writing as k1 square and this as k2 square. That means our k1 square is 2m by h cross square minus b plus v0 and k2 square is 2mb by h cross square. These general solutions, the general solutions of 9 and 10 are, it's not these, just the general solutions of equation 9 and 10 are. So this is equation number 9. And this is similar to your harmonic oscillator equation. So it will be either a sine function or cosine function. That is true there. And a solution means, suppose you are substituting that solution in this equation, it will be satisfied. That means you will be getting 0. So sine and cos both are possible. And in the terms of mathematics, the general solution will be a sum of those two. So both can be a solution. So you are taking it as the sum. So that is why it is a sine k1r plus b cos k1r UR for r less than capital R. And for the second region, this is like our charging and discharging of capacitor etc. equation, where we have the exponential equations. So it is u of r is c e raised to minus k2r plus d e raised to k2r. So they are either minus k2 or plus k2, both are possible. And now from this general solution, we have the constants a, b, c, d, etc. Now what we can do is to keep the wave function ur finite. That means you have Deuteron, and that Deuteron r is the distance or separation between the particles. That r cannot be equal to 0. That means in that case no particles exist or no such cases exist. That means when r tends to 0, there is no possibility of existing the Deuteron, which means that the probability must be 0, and probability is normally square of the wave function. So that wave function should vanish. And here we are taking the wave function as ur. Actually, it was psi r, which we have rewritten as ur by r. So ur must be, or psi r must be equal to 0 when r tends to 0. In the similar way, at infinite distance, there is no, when two particles are at infinite distance, or when the distance is very large, you can say that there is no interaction between them, or that system does not exist, which means that there also our existence of that system 0 means wave function is 0. So we have the two conditions. So in other words, you can say that it must be a finite value at infinite distance, and not it should be tend as infinite. The probability of occurring a particle is infinity is not possible. The maximum value is between 0 and 1. So for keeping u of r is equal to 0, for when r tends to 0, in this equation, when r is tending to 0 or r is equal to 0, you can say that ur must be equal to 0. So here you can see when r is equal to 0, sine 0 is 0. But in case of cos, that value is cos 0 is 1. So this cos k1r is 1 when r tending to 0, and at r tends to 0, this ur must be tending to 0 or ur should be equal to 0. This is possible. Sin k is already 0. So this is possible only when this product is 0. Here this number is 1. Cos k1r, it is nearly 1 or it is tending to 1. So the possibility of this becoming 0 is only when this b is 0. When b is 0, that is true. So this b must be equal to 0. So our solution will have only this value a sin k1r. And here we have mentioned that when r is tending to infinity, you can see that in this term it is e raised to minus k to r, that you can write as c by e raised to k to r. And when r is tending to infinity, it is e raised to infinity, and e raised to infinity is infinity. So a number by infinity, it is 0, or it is a finite number, that you can say. And here it is d e raised to k to r. When r is infinity, e raised to k to infinity or e raised to infinity is infinity. That means ur will be infinity when this r is tending to infinity. So this term e raised to k to r is tending to infinity. But our function should be a finite one. That is possible only when this d equal to 0 or this is not existing. So this should not exist to get the conditions, and also this should not exist. So now we have b is equal to 0 as well as d is equal to 0. So now we can write as u of r as a sin k1r for r less than r, and ur as c e raised to minus k to r for r greater than capital R. And this psi of r must be bounded and continuous. We have mentioned that it is a bound system and it should be a continuous one. That means if a system is existing between a limit, that means between a value, so that system should exist at all points between the value. Suppose you are saying that the size of your Deuteron is say 2 Fermi or 4 Fermi, whatever maybe. So between that value there must be Deuteron. So at a point say 1.5 Fermi, if that psi r is equal to 0, which means that at that point, or when the distance between the particles is at that 1.5 Fermi, there is no Deuteron. Such case is not possible. So the probability of occurring this Deuteron at a particular distance, it should vary from that values, a minimum value and a maximum value between these extreme values. That means your psi r should be a continuous function between the bounded values. It must be bounded, that means it must be between two values, and between that values it must be continuous. That is the meaning of this sentence. So it has a continuous derivative everywhere. If a function is continuous, then its derivative should also be continuous. Then only your equation d square u by dr square etc. it will be valid. And at r is equal to capital R, both psi r means psi r is equal to, you are writing as ur by r. So both psi r and ur and their first derivative should be continuous. Means that from one region to the other region you are entering at r is equal to r. So that function must be continuous there. Without any break, it must go from one region to other region, and also the first derivative of the function should be continuous. So at boundary, that means that r is equal to capital R, you can write as u is equal to a sine k1. That small r is now replaced with the capital R. Its differential of sine k1 r is cos k1 r into k1. So du will be a k1 cos k1 r. And already you have an equation u is equal to c e raised to minus k2 small letter r for r greater than capital R. At r, it will be capital R, e raised to minus k2r, then only it will be continuous. So du will be equal to, differential of this is e raised to minus k2r into minus k2. So it is minus c k2 e raised to minus k2r. When u is continuous at the boundary, you can write as a sine k1r equal to this c e raised to minus k2r, that you are marking as 13. And when du is continuous, this a k1 cos k1 r must be equal to minus c k2 e raised to minus k2r as equation 14. If you are dividing this 14 with the 13, dividing 14 by 13, you will get it as k1 cot k1 r is equal to minus k2. You can see this. Dividing this with this cos by sine you are taking as cot. Only k1 here, a cancels, here c cancels, there is a minus sign here and k2 here. So our equation is k1 cot k1 r is equal to minus k2. This equation gives an implicit relation between binding energy B of the two nucleon system to range of potential R and depth V0. So this K1, actually we have written that K1 in terms of B and V0, this K2 in terms of V, and also this actually you have an R here. So this relation connects the range of potential R, depth V0 and binding energy. And the binding energy B is non-experimentally. We have already mentioned, or we have already calculated it. It is nearly 2.225 MeV. Still, there remain two unknown parameters, capital R and V0 in a single equation. We have only one equation, but you have two unknowns. So, it cannot be solved using a single equation. In order to solve, we must have one more equation relating to R and V0. In other words, the transcendental equation, that term is known to you, which cannot be solved analytically, but may be solved graphically. So, one way of solving it graphically is you plot this function and this function, and when you are plotting the functions, at a particular point, these functions will meet. The graph will meet, and that meeting point will be the solution of the equation. And that is the general method you are using. That is a graphical solving one method. So, there is another method. We may choose an arbitrary value of R and find V0 and vice versa. You can give some value of R and you can solve it. There is another way. Now, to find the relation between V0 and R, we are rewriting our equation as, we got the equation as K1 cot K1 R is equal to minus K2. You are taking this K1 from here to here. So, cot K1 R is equal to minus K2 by K1. Now, in the right hand side of equation, you are substituting for K2 and K1. Our K1 square was 2m into minus b plus v0 by h cross square. So, you are taking the square roots. So, K2 is root of 2mb by h cross square, and K1 is 2m by h cross square minus b plus v0. So, this h cross square cancels. So, it will be root of course, with the minus sign, minus root of b by v0b. And V0 is the potential, and already we have mentioned that this binding energy of deuteron is very small. So, you can neglect this B in comparison with the V0, since V0 is much larger than B. That means your cot K1R can be written as minus root of B by V0. And this equation number 16 suggests that cot K1R is small and negative. How can you use that? Because this is a negative value, and this B is much smaller than V0. That means it is a very small value. So, your cot K1R must be a small one. Its magnitude is very small. This is giving you the magnitude. The magnitude is very small, and also it is a negative quantity. So, this knowledge, or using this knowledge, you can say that K1R is slightly greater than pi by 2. How it is possible? This figure will explain that. This is normally you have the variation of sin x, cos x, tan x, etc. This is known to you. Your sin x is varying like this, a sine function. A cos x is varying like this. Okay, and we know the variation of tan. Tan is like this. From 0, it is increasing here. And we know these are the values 0, pi by 2, pi, 3 pi by 2, and 2 pi. And our cot KR, cot you are taking as cos by sine. And for 0, sine 0 is 0 and cos 0 is 1. So 1 by 0 is infinity. That means for 0, the value is very large. We are not getting, or you can't mark it in the graph. And at pi by 2, we have to take cos by sine. Cos pi by 2 is 0, sine pi by 2 is 1. So 0 by 1 is 0. And at pi, cos pi is minus 1 and sin pi is 0. So cos pi by sin pi you are getting as minus 1 by 0, and 1 by 0 is our infinity, or you have a minus sign there. So you are taking it as minus infinity. And again, when that pi greater than 0, value changes from negative to positive. So in quadrants, you know that in the first quadrant, 0 to pi by 2, cot is positive. In the second quadrant, as you know, only sine is positive, cos negative. It is becoming a negative value. And the third quadrant, both cos and sine are negative. So this is becoming positive. And the fourth quadrant, your sine is negative, cos positive. So again you are getting a negative value. So this repeats. So we have just mentioned that the your cot K1R you can write as root minus root of B by V0. That B is very small compared to V0. So that V0 by B is a very small value. So only in this region you are getting small values. Here large values are there because from 0 it is increasing. And the second thing is that it is small and negative. Its magnitude is very small and it is negative. So when it is less than pi by 2, it is positive value. When it is greater than pi by 2, it is negative value. So you can say that cot K1R is slightly greater than pi by 2. Or this is also same, also true. Cot Kr is slightly greater than 3 pi by 2. And that we have mentioned here. Therefore, K1R is slightly greater than pi by 2. And the same solution you will be getting if you are plotting that K1 cot K1R and K2. You will be getting a similar result. So that is we got as K1R is nearly, we have mentioned that slightly greater than pi by 2. You can take it as pi by 2 itself. Nearly pi by 2 or 3 pi by 2, etc. Or you can write K1 as pi by 2R or 3 pi by 2R, etc. And also we have a relation K1 is equal to root of 2m into V0 minus B by H cross square. And since this V0 is much larger than B, we are dropping this B. So K1 is equal to root of 2m V0 by H cross square. So comparing, your root of 2m V0 by H cross square will be equal to either pi by 2R or 3 pi by 2R, etc. Squaring, 2m V0 by H cross square is pi square by 4R square or 9 pi square by 4R square, etc. And taking the first value, you can write as 2m V0 by H cross square is pi square by 4 pi R square, or V0 R square you can write as pi square H cross square by 8m, or V0 you can write as pi square H cross square by 8m R square. And taking the reduced mass of deuteron m, how can you calculate m? Deuteron mass will be, suppose m1 and m2 are the masses, it will be m1 m2 by m1 plus m2. And if you can take the proton and neutron mass are approximately same, that reduced mass will be equal to m by 2. You know the mass of proton as 1.00078 U. So it will be that value divided by 2. That will be the value of m. And considering this capital R is equal to 2.1 femtometer. These are some experimental data that we are getting. It is the sometimes it is known as the RMS value of the radius of deuteron, etc. That value is nearly 2.1 femtometer. This is femtometer means it is, or you can write this femtometer as Fermi, 2.1 Fermi. That is into 10 raised to minus 15 meter. This femto stands for the 10 raised to minus 15. So you can substitute this H cross square, m, r, etc. Then V0 can be calculated as 35 MeV. So the potential of your nucleon system you can calculate as 35 MeV. And this is, that means that minus V0 means minus 35, and our binding energy is nearly 2. And by knowing this, we have in the previous figure, you have marked V0 as in very deep position and your B in the topmost position of that graph. And now, the deuteron wave function is drawn in figure that we have just mentioned. So, the deuteron wave function should be continuous, and in the first region it is a sine function, and the second region it is an exponentially decaying function. So the deuteron wave function for R is equal to 2.1 femtometer. This is 2.1. Note how the exponential function joins smoothly to the sine function at R is equal to R. This is our sine function. Actually, it will be like this. But at R is equal to R, it is joining with, because you have R, small r greater than capital R, it is exponential. So it is the exponential decay. And that's all in this class. Thank you.